Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. Today in this video we're going to look at some Boolean expression terminology that will allow us to better describe our Boolean expressions and how they relate to gate diagrams as we move forward in these lessons. Alright, let's get started. So we're looking at Boolean expression terminology. So first let's go ahead and write a Boolean expression. Actually we're going to write two. And you'll see that there's going to be a difference in their form, which we will look at. Okay, so in this Boolean expression we have, we would read this as W naught and Y naught, or X and Y naught Z, or W naught and X and Z. And typically we kind of shorten that to something that looks like this: W naught Y naught, or X Y naught Z, or W naught X Z. So the ands are dropped and just kind of read them together, just how they look in the expression, just right next to each other. And so that's my experience there. And then we'll do the second one. And so we would read this as W naught or X naught and quantity Y or Z naught. And so we could probably do that actually the first thing, quantity as well, quantity W bar. There's another way that we say naught is just the bar because of the bar that's over there. So W bar or X bar and quantity Y or Z bar. So we can read it in that way so people understand what we're trying to write. And so let's identify a couple of things here. So first off, we can see that we have these individual instances of our variables, all these underlined green ones right here. Okay, these are called literals. And so we can define them as every instance of an input variable. And this is complemented. That means barred or knotted or not. So we have different number of inputs that are going into our logic gate network, and our Boolean expression is describing that. And one thing that you'll kind of might guess right away is that as a designer, I want the fewest number of literals as possible because that would simplify my digital logic circuit. And then from a manufacturing point of view, that means that it's going to cost less money to make that. And so, there's a sort of an optimization strategy that looks at one aspect is, minimizing the number of literals in our expressions. Second definition here is a term. So we have these groupings and these are called terms. Oops, not terms, terms. There we go. And so this is kind of a little bit more generic. So these are groupings of literals. Oops, sorry about that. Or other terms. Get my finger off that button. Okay, so groupings of literals or terms. And I think that's as specific as I want to go. So you kind of just got to look at this and say, okay, how are these grouped together? We can see we have a grouping of and operations here, and operations, and operations. These literals are grouped by an or operation and or operation. And so they actually get a name because of that. So since it's grouping, this term is a grouping of and operations, we call this a product term. And this grouping is of or operations, we call that a sum term. And so this would be a sum term. And these would be product terms because of the and the or respectively. Okay, great. So let's continue here and talk about these two forms, because there's obviously a difference between them. So let's talk about that difference. So this first one, well, actually let's identify first number of literals and number of terms. So F1 has 3 terms, and they are product terms with, and I can count them here, 1, 2, 3, 4, 5, 6, 7, 8. And I don't care about repeats, it's every instance that shows up. So this is 8 literals. And as always, you know, it's nice for you to kind of jump ahead and say, okay, what about F2? And you can answer that question before I do, and then you can check your understanding. And so F2 has 2 terms, and it has 4 literals. All right, so in looking at these two, F1 and F2, if I know nothing else about them, then I can make an assumption that it's going to be easier to implement F2. It's going to cost less to actually build F2. And so just because it has fewer terms and it has fewer literals. Okay, let me just recopy our expressions here. So we got WY or XYZ or WXZ, and then we got complements for those. Okay, F2 is WXYZ, and we have complements over WX and Z, bars over those 3. Okay, so those are just a repeat of our 2 expressions. And so let me introduce 2 other terminologies. So this is sum of products. Can you guess which one is sum of products? And so sum of products means that first we have product terms. So these would be and terms, and then we OR them together. And those would be the OR terms. And so that would be, or I guess this would be sum them together. And so F1 is our sum of products form. So we have product terms, these are ANDed together. And then we take all those terms and OR the terms together. Okay, so we have product terms that we sum together. And so product of sums, which is the other way we can look at it, that belongs to F2, or F2 belongs to that group. And so first we have a set of sum terms, which are ORs. And then we product them. I'm going to use that improperly. Product the terms together. And that would be and. So that's how we're doing this here. So we have a bunch of sum terms, and then we product them together. So F2 shows that. So we have a sum term, we ORed them. And there's a sum term, we ORed them, and then we take that whole term from both sides, both those terms, and we AND them together. So that would be product of sums, and so we have sum of products and product of sums. Alright, so that's it for this lesson. I hope that clarifies some of the terminology that we use for Boolean expressions. As always, I appreciate you being here. Thanks for watching the video. If you could like and subscribe to my channel, I'd appreciate that. I'm Mike Stanczyk. This is Digital Electronics Classroom. Have a nice day.